a FastAPI checkout service OOM-killed every 2 hours. Memory grew linearly because each request created a new database engine with its own connection pool. Let's break down FastAPI Async SQLAlchemy, Alembic migrations and production patterns, how it works, and the exact mistake behind that failure. Async SQLAlchemy lets your FastAPI endpoints make database calls without blocking the event loop. Instead of waiting for the database, the event loop can handle other requests. This is achieved using an AsyncEngine and async sessions. Using sync SQLAlchemy and async endpoints defeats the purpose. Each sync call blocks a thread, and if your DB is slow, threads pile up. I've seen a service with 10 workers and 20 DB connections handle 50 rec/s before the thread pool exhausted. The fix is to use SQLAlchemy's async extension. Here's the correct way to set up an AsyncEngine. Create it once at startup with a connection pool. The session factory creates new sessions per request. Never create an engine inside a request handler. The session is your transactional boundary. Every request gets one session, uses it, and closes it. Leak a session and the connection stays in the pool, eventually exhausting it. The pattern is to use a dependency that yields an async session and closes it in finally. This dependency creates a session, yields it to the endpoint, commits on success, rolls back on error, and the context manager ensures it's closed. Always use async with to guarantee cleanup. Alembic migrations run synchronously by default. That's fine for maintenance windows. But if you need to run migrations against an async engine, use runAsync with a function that gets a sync connection via SQLAlchemy. This avoids creating a second engine. This env uses the same async engine as your app. It creates a sync connection via runSync to run migrations. Note the null pool for migrations to avoid pooling issues. Running migrations while the app is live is risky. DDL statements can lock tables and block reads writes. Use op, execute, set lock timeout equals 5,000 to abort if the lock can't be acquired within 5 seconds. For indexes, use PostgreSQL concurrently equals true. This migration adds a column safely. It sets a lock timeout, adds the column as nullable first, then backfills data and sets not null. Always test rollback. Migrations that work on your laptop fail in production because of different data, indexes, or permissions. The fix is to test migrations against a copy of production data in CI. Always test both upgrade and downgrade. This script runs migrations, verifies the schema, and tests rollback. Always test downgrade -1. Many developers only test upgrades. A failed rollback means you can't undo a bad migration without manual SQL. Default pool size is 5, which is fine for development but will choke under load. The right size depends on your DB's max connections and your app's concurrency. Rule of thumb, pool size equals max DB connections / number of app instances, 0.8. Here's a production-ready pool configuration. Pool size is 16, max overflow allows bursts, pool preping checks connection health, and pool recycle is set to 240 seconds, 4 minutes, to avoid stale connections. Async SQLAlchemy adds complexity. If your app is CPU-bound or has low concurrency, sync is simpler. Profile your endpoints first. If the bottleneck is CPU, async won't help. Use async when you have many concurrent DB calls or are integrating with other async services. For simple CRUD with low traffic, sync is fine. Profile first. This is the same issue we highlighted at the start. Here's exactly why that happened. Every request created a new AsyncEngine via create AsyncEngine in a dependency. The engine's connection pool never got disposed, and each engine held 5 connections open. After 1,000 requests, 5,000 idle connections consumed all memory. Creating a new AsyncEngine inside each request handler creates a separate connection pool per request, exhausting file descriptors and memory after many requests. The fix was to move engine creation to app startup, at app on event, startup, with a single engine equals create AsyncEngine, used async session maker as a dependency, added engine dispose on shutdown, 1 engine per app lifetime. Never create an AsyncEngine inside a request handler. Each engine creates its own connection pool. After enough requests, you'll hit OS file descriptor limits and memory exhaustion. One engine per app lifetime. Don't create a separate sync engine for Alembic. Use runsync on your AsyncEngine. Two engines mean two connection pools, twice the memory, and potential deadlocks if both try to access the same schema simultaneously. Always test Alembic downgrade -1. Many developers only test upgrades. A failed rollback means you can't undo a bad migration without manual SQL, a nightmare during an incident. If pull recycle is longer than your DB's wait timeout or idle in transaction session timeout, connections will be dropped. Set pull recycle to 80% of the DB timeout. For PostgreSQL, check show idle in transaction session timeout. The run async pattern shown requires Alembic equals 170. Earlier versions lack runsync on async connections. If using an older Alembic, create a separate sync engine for migrations or upgrade Alembic. The article mentions using depends with yield, but doesn't show the full pattern with explicit rollback. Here's a robust dependency that commits on success, rolls back on error, and always closes the session. The article sets expire on commit equals false, but doesn't explain why. In async, accessing expired attributes after commit triggers a lazy load outside a session, causing an error. This setting keeps objects usable after commit, which is essential for returning ORM objects from endpoints. The article recommends max overflow equals 10, but if your database has a hard connection limit, e.g., 100, ensure pool size plus max overflow per instance times number of instances stays under that limit. Otherwise, you'll get fatal, too many connections errors from the database. To debug session leaks, add logging to track session creation and closure. Use a custom async session subclass that logs when it's created and closed. Also monitor pool status via a health endpoint. If checked in connections is growing, you have a leak. Let's run through some common interview questions. How does async SQLAlchemy handle connection pooling differently from sync? Async uses a single pool shared across event loop. Sync creates one per thread. When would you choose async over sync? High concurrency, 1000 rec/s, or many I/O calls per request. What happens when you create an AsyncEngine inside a request handler? Each engine creates a new pool, exhausting file descriptors and memory. And a few frequently asked questions. How to run Alembic migrations with AsyncEngine? Use run async in env, pi with engine syncEngine. What is the difference between async session and session? Async session uses a wait for execute, must be used with AsyncEngine. How to avoid connection pool exhaustion? Ensure sessions are closed, set appropriate pool size, monitor pool usage. To recap, never create engines in request handlers. Always use async with for session lifecycle, set pool recycle to 80% of your DB's idle timeout, and test migrations against a production data copy in CI, including rollback. Ready to go deeper? Up next, FastAPI Cloud. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.